There is nothing new to be discovered in physics. All that remains is more and more precise measurement. Right. So that was British physicist Lord Kelvin back in 1900, speaking with just, well, supreme confidence. But if you know anything about physics history, you're probably hearing a massive record scratch in your head right about now, because Lord Kelvin was about to be proven wildly, spectacularly wrong.
Welcome to this explainer. Today, we're strapping in for a really high-speed journey through the 5 fundamental physics laws that built, and honestly, in some cases, completely broke our understanding of the universe. We're going to start with the solid physical world you can actually touch and feel, and then we're going to accelerate all the way down into the mind-bending, totally rule-breaking quantum realm.
Okay, Section 1. Physics of the everyday, the macro world.
So think about the heavy thud of a physical impact, or the sheer literal force of a rocket leaving the launch pad. This is classical mechanics. It's the physics of the observable world, the comforting rules that govern everything we interact with every single day. But to really get a handle on it, we need to anchor ourselves in the 1600s, the absolute birth of modern experimental and theoretical physics. In just a 25-year span, 2 monumental discoveries completely laid the groundwork for how we understand physical reality.
First up, Sir Isaac Newton publishes his groundbreaking Principia in 1687, gifting us Newton's second law. Basically, it states that if a net force acts on an object, it gives it an acceleration directly proportional to the magnitude of that force. Think about the pure physicality of that. You push something heavy, it moves. The harder you push it, the faster it accelerates. It's just the literal, direct translation of force into motion.
And what's absolutely fascinating is how that single 17th century classical law underpins virtually all of our modern transportation. Every time you hear the screech of tires from a sports car, the blur of a high-speed bullet train, or the supersonic blast of aerospace engineering shooting space shuttles into orbit, that is literally Newton's second law in action. It is the absolute bedrock of all mechanical engineering.
But actually, before Newton, there was Robert Boyle in 1662. Boyle's law tells us that gas pressure is inversely proportional to its volume, as long as temperature and mass are constant. Imagine physically squeezing gas into a tiny cylinder. As you shrink that space down, those gas molecules are slamming against the walls faster and harder, forcing the pressure to just absolutely skyrocket. Less volume equals massive, explosive pressure.
Now, the crucial thing to remember here is that these are extreme physical forces. Testing the absolute limits of force, pressure, and volume can get pretty dangerous in the real world. That's why it's so cool how modern learners are using platforms like PraxiLabs. They've built these 3D virtual sandboxes, letting students safely run intense physical experiments like testing explosive gas pressure or crazy mechanical force, right from their laptops in a completely safe, risk-free environment.
Moving on to Section 2, the power of relativity. Mass becomes energy.
All right, brace yourselves, because we are leaping into the 20th century. This is where those comfortable, predictable rules of classical physics get dangerously explosive. The year is 1905, and Albert Einstein, the father of relativity, publishes a paper asking a profoundly simple question. Does the inertia of a body depend upon its energy content? What he proved there absolutely shattered our understanding of the universe. He showed that mass and energy aren't just related, they are literally 2 sides of the exact same coin. Mass can transform into energy and energy right back into mass.
And the real-world implications of this mass-energy equivalence? Staggering. By unlocking the energy stored inside just a tiny amount of mass, humanity accessed unprecedented power. Historically, this very equation was utilized to create the atomic bomb, a weapon of just immense destruction that resulted in the deaths of over 200,000 Japanese people during World War II. Yet, to put things into perspective, this exact same physics principle is harnessed peacefully today to generate massive amounts of electricity through nuclear power. It's a profound look at how physics actively shapes human history.
All right, Section 3, entering the quantum realm, the micro world.
We are now descending way below the level of the atom into a totally invisible reality. If we compare the two, on one side you have classical physics. It's predictable, macroscopic, plays nicely by Newton's rules. You push a block, it slides. Easy. But on the other side, quantum physics. When scientists first started zooming in on electrons orbiting a nucleus, they realized these particles were acting entirely erratically. They were jumping around, behaving in ways that completely broke the laws of classical physics. It absolutely stumped the greatest minds of the era.
And here is where things get truly weird.
Max Planck discovered that energy doesn't flow in a smooth, continuous wave like water out of a garden hose, which, by the way, is what pretty much everyone thought at the time. Instead, as Planck's equation defines, energy transfers in these discrete, tiny, choppy packets. He called these quantized parts quanta. He basically shattered the illusion of a smooth universe, proving it's actually incredibly pixelated down at the microscopic level.
To put that into perspective, just think about this infinitesimally small number, 6.63 times 10 to the negative 34th power joules times seconds. That is Planck's constant, usually just represented by the letter h. It is staggeringly tiny, but it is the ultimate master key of the whole quantum world. If you know a photon's wave frequency, you just multiply it by this exact constant and boom, you've calculated its precise energy. It's a real game changer.
But you might be wondering, how do you actually map the movement of these erratic, totally unpredictable particles over time? Enter Erwin Schrödinger, an Austrian physicist who won the Nobel Prize back in 1933 for his famous equation. Schrödinger's equation is essentially the quantum equivalent of Newton's laws. It's a highly complex partial differential equation that calculates exactly how the quantum state of a physical system changes as time moves forward, finally letting us tame the seemingly impossible behavior of the microscopic universe. Now, quantum mechanics is intensely, staggeringly complex. But again, we're lucky to live in an era where you don't actually need access to a multi-billion-dollar particle accelerator to explore these ideas. Interactive online simulations, like the ones from PraxiLabs, let university students and researchers run advanced chemistry, physics, and biology experiments virtually. It just makes diving into the subatomic world deeply accessible, no matter where you happen to be.
And finally, Section 4, the endless physics frontier.
As we pull all the way back from the microscopic pixels of quantum mechanics out to the massive observable universe, we really get a sense of the incredible scope of human discovery. From Newton's forces, to Einstein's explosions, to Schrödinger's probabilities, we've mapped an unimaginable amount of reality in just a few short centuries. Which brings us to a final thought. Think back to Lord Kelvin at the very beginning of this explainer. In 1900, he proudly declared that physics was finished. Yet relativity and quantum mechanics were hiding right under his nose, just waiting to absolutely break the universe as he knew it. So I leave you with this question. If they were so blind to the truth back then, what massive invisible realities are we entirely missing today? What uncharted depths of the universe are just waiting for the next great mind to discover? Thanks for joining me on this explainer. Keep questioning everything, and I'll catch you next time.